So you're recording. Okay, it says be sure to let everyone know. That's fine. And so hopefully now you can see the first page there. So if you can't see that, it's probably a good time for me to find out. So Brendan, everyone, are we okay? Can we see the screen that I'm sharing?
Yeah, we can indeed, Richard. Yeah.
Yeah, it's all good. Yeah, okay, super. Thanks, Lizzie. Right, okay, so straight into it then. Question 1. Let's have a look what we've got. Looks fairly complicated to start with. So it's been a while since we've done organic chemistry. Things I would be looking for straight away here. So let's just get my highlighter out. So maybe not an obvious one, but there we've got. Oops, let's change pen, Richard. Great start. Okay, so I've got an Ester link in the first one, and I can see that I've hydrolyzed that ester. This molecule there has turned into the alcohol, and then that part there turned into the carboxylic acid derivative. So we've got the salt there of the carboxylic acid. So let's go down to the first part of the question. So give the reagent and conditions for step 1. Well, we've probably got 2 methods that we know about for hydrolyzing an ester. So I would imagine the 2 things that we're wondering about. So is it an acid? Is it an alkali? Well, the clue here is coming in the fact that we've made the salt of the ester. So if we were using the acid, then we would go back to make the carboxylic acid. So that's telling me that rather than doing acid hydrolysis, we're doing alkaline hydrolysis, which is going to inform me of the reagent. So give the reagent. Just be careful about putting things like, so quite a common answer here would be hydroxide ions. Yeah, it is going to be hydroxide, but that in itself isn't a reagent. So the thing that we're going to go and get from the bottle needs to be sodium hydroxide or potassium hydroxide. It definitely needs to be aqueous, so we don't want anything that's too concentrated. So aqueous would be good, or dilute would be good. If you wanted to go for a concentration, I'd be looking at something reasonably concentrated, but not particularly. And I'd probably put heat and reflux, or some idea that you warm this up. State how you could obtain a sample of the alcohol from the reaction mixture in step 1. So at the end of the reaction, we have a salt and we have the alcohol. So we need to separate these, and we're going to separate them in terms of the boiling point. So I think a fairly safe answer at this point would be some kind of distillation. Fractional distillation would be fine. Not a topic that we've really done much of yet, but you might have got away with chromatography. Not a brilliant method here if you want to keep the alcohol as a product. So distillation would be the safe answer, not just evaporation. And I think there I've covered what I will be looking for the marks. So let's have a look at the mark scheme for this. Not coming across great, so sorry about the image that we've got there, but we can see, so sodium hydroxide, yeah, well, we'll definitely put that. So we needed to get that reagent right. If you'd have put hydroxide, they would have marked on, but you wouldn't have got the reagent mark. Potassium hydroxide would be absolutely fine. Barium hydroxide would be fine. You're moving on to fairly dodgy ground if you're talking about calcium hydroxide or magnesium hydroxide. They're not particularly soluble, so would be a poor choice really of hydroxide. You can see there all they were looking for the second mark was for it to be aqueous, and so in mentioning our concentration we got that across as well. They've not even been that bothered that we warm it up, so it was just the fact it was aqueous, and you can see there we've said distillation, so that's fine. So they weren't bothered if we said evaporation, not good enough, certainly not reflux, and they've accepted chromatography. So hopefully we've got off to a good start there. 3 marks. You can see that for this question, then we didn't enter into steps 2, 3, and 4, where it was maybe getting a little bit more interesting for another day, perhaps. Okay, right. Question 2. Quite a lot more going on here with question 2. I think when students see these, it's often fairly scary. So when they see these sort of large facts, just wondering where to go with it. As soon as you see that, you probably know that you're looking at this triglyceride question. It might be biodiesel, it might be soap. At the heart of these questions, always, and they tend to be sort of written out the same in terms of the left-hand side of the molecule, we have what will ultimately end up being our glycerol. And this is important just to establish that in terms of what our ester links are going to look like. So it's difficult to draw these nicely, but what you often won't see here is the 3 ester links. So I'm just going to highlight those now so we can see, because the ester links go in reverse of how we normally draw them. So probably in your notes, when you draw your ester link, you'll draw it like that. But here, as we've got our triglyceride drawn, we can see that that oxygen is on the other side, like that. So those are our 3 ester links. What we're going to do here, write an equation for the reaction of this with sodium hydroxide. So we're going to, as we saw in that previous question, we're going to, and this time remember, our molecule is like this. So we're going to break those 3 ester links. So we want to go down our 3 ester links, and we're going to reform glycerol, which is the propane 1,2,3 triol. So down here, I've got plenty of space to draw my answer, so I'm just going to draw my propane 1,2,3 triol. And then I'm going to go back, and these are going to become carboxylic acids. So you can see that my chains are a different number of hydrogens each time, the same number of carbons, so that means that there's a different degree of saturation to each of these chains. So I've got 3 chains. I'm going to write them the other way around. So I'm going to put C17H31, and then my acid group. Like in the previous question, I just need to be mindful that I'm not going back to make the carboxylic acid, but rather I'm going to make the salt of the carboxylic acid when I hydrolyze that. So that's the first of my soap molecules, and then I've got one with 33, C17H33, again, COO minus, Na plus, and then the final one with even fewer hydrogens, so probably a couple of double bonds in this one. Like so. Now this will have required 3 sodium hydroxide molecules to do that. So there is my overall balanced equation. So I'm fairly happy with that. Just double check. So that's looking good. So that was worth 2 marks. And then give the formula of the biodiesel molecule with the highest MR. Right, so we're back to the original triglyceride. Now when we make biodiesel, so this is a transesterification reaction, so we've got our long carbon chain, and then we make the methyl ester of it using methanol. So I'm going to be looking at that. And now I just need to pick the carbon chain which would give me the greatest MR. And I can see that the one with 33 hydrogens, so the one with fewest double bonds, will work. So I want to have C17, H33, COO, and then I've got my methyl group on the end. So give the formula of the biodiesel molecule. So it's not asking for a molecular formula. Might have got away with a molecular formula for that, but a molecular formula wouldn't really give us any idea of what the structure is. So I think that's a safer answer. Okay, let's have a look at what the mark scheme would have wanted for this. So again, there we can see, so the left-hand side of our equation would give us 1 mark. I mean, they'd started that off for us anyway, so we just needed to get the fact that there were 3 sodium hydroxides, and then 1 mark for the right-hand side. So we've got our glycerol, and then those 3 soap molecules. You can see they've not put the charges in. I did put the charges in. If you are going to put the charges in, make sure that you put both the negative and the positive charges in. And certainly also it said don't put a formal bond in between the oxygen and the sodium. So that would be a crime. And then we've got our biodiesel molecule at the end. They've allowed the molecular formula. We said we weren't as happy with that, so we've picked the mark up for our structure of the methyl ester. Okay. On to question 3. This is pretty tricky, and it's a nice style of question. You'll see this quite a lot. It's a problem-solving organic, involves lots of different things, and there's clues there. These can often be the ones where you might sit and with a bit of pen and paper sort of scribble away trying to work out what the right answers are, and you'll go back to the drawing board, and quite often if it's not arriving, these are good questions just to sort of leave alone for a few minutes and then come back to at the end when you've got a bit of time. So don't panic about them. The answer might not arrive immediately. Worth just having a read through the information that we've got. So they all share the same molecular formula, C5H8O2. Obviously all our structures have got to comply to that, and then we've got to come up with 4 different structures. The first one is probably the most cut and dried one. So this, either we get this right or we don't. So this is the structure of an ester, and it's an ester with a methyl group. So down here, I'm going to have a look at what L is. So I have a methyl group, and I'm just going to put my methyl group on the end there, and then the rest of my ester can start. You can see I've already used up 2 carbons, so I've only got 3 more carbons to play with, and I've got 2 methyl propenoate. So propenoate. Now what that's suggesting is that I've got a carbon-carbon double bond between those 2 carbons there, and for it to be 2 methyl, then on my second carbon of my propenoate group, that being 1, that being 2, and that being 3. It doesn't leave me an awful lot more to play with, so I've now got 1, 2, 3, 4, 5 carbons. You can see in terms of my hydrogens, I've got 3, 6, 7, 8, and I've got my 2 oxygens. So a bit of a strange one that to start with. So not an ester that will come across very often, but that's my answer to L, and there's only one correct answer for that. The next one, an ester which shows EZ stereoisomerism. Now I think we can see that if we're playing around with this number of carbons, hydrogens and oxygens, and it is an ester or a carboxylic acid, it's going to be an unsaturated one because I don't have enough hydrogens to make it. So if this was pentanoic acid, then we would expect it to have 10 hydrogens in there. So an ester with EZ stereoisomerism. I think probably what I would be doing for my answer here, so here I am doing M, for it to have EZ, now this might not be the right place to start, but I think I would probably attempt an alkene like so, and if I put my hydrogens across from each other, I know that I've got a couple of carbons left. I know that it needs to be an ester, so I've got a little bit of room for manoeuvre here. I think probably what I would do is just do that for my ester, just play it safe. It's definitely got EZ isomerism. You can see that the one that I've drawn here, the groups with priority, so this carbon and this carbon, so I've drawn the E isomer. It's not saying that I need to draw the E or the Z, so I'm okay there. Again, does it match the formula? So I've got 1, 2, 3, 4, 5 carbons. So that's looking good. I can see my 2 oxygens, and I've got 3, 4, 5, 8 hydrogens. So happy with that as my answer for M. There will be several other answers for that as well. So, for example, where I came to here, I could have drawn my ester going the other way around. So I might have chosen to do that. And so just reverse my ester. That would have been absolutely fine as well. And I'm sure that there'll be a few other answers for that as well. So next, N, I'll do this in green. So this is a carboxylic acid with a branched carbon chain. Doesn't show stereoisomerism. Okay, right. So I'm just going to crouch down to do this. So good place to start. Put my double bond in. Doesn't show stereoisomerism. Well, I think this would be a good place to start now, because that immediately means it's got a branched carbon chain, and it means it won't have EZ stereoisomerism. Of course, that's not the only kind of stereoisomerism. I just need to be careful that I don't end up putting a chiral carbon in and giving it optical isomerism, but I'm feeling fairly happy that it's not got EZ. And I've used up 4 carbons so far. Let's make it a carboxylic acid, because I've only got 1 carbon left. So there's 1, 2, 3, 4, 5 carbons. I've used up so far 7 hydrogens. There's my 8th hydrogen. So that works for this. And again, I'm sure that there will be perhaps some other examples that you could make where it's branched. I would imagine that the place to start that would be to make the groups attached to the left-hand carbon of the double bond. If you made those hydrogens, then you'd have been able to get some branching in the carbon chain and keep it a carboxylic acid. Just make sure that you didn't make it into a chiral carbon at the same time. Right, okay, so we're going along nicely. And then the final bit, we want an optically active carboxylic acid. So where would I start with this? Well, I think I'd probably start by giving myself a carbon. For it to be optically active, I need a chiral carbon, and I think that's where I'll start this problem. So that means it needs 4 different groups attached. It would be sensible for one of my groups to be a carboxylic acid group. And I've used up 2 carbons. I've got 3 left. And I also know that these compounds have been having carbon-carbon double bonds in. So I think perhaps after my CH3, with 2 carbons left to play with, I think I'll include my alkene group. So let's just have a quick count up. So we've got 1, 2, 3, 4, 5. So I've exhausted all my carbons. 1, 4, 5, 6, 7. So 1 hydrogen left. Well, isn't that fortunate? So that gives us our molecular formula of C5H8O2. As you can see, it has the chiral carbon, so that carbon is attached to 4 different groups, and that fits the bill. I'm not sure if you'd have been able to draw anything other than that for P. Okay, let's have a look at the mark scheme and see if we got those right. So L, we said that there's pretty much only one thing we'll be able to draw there. You can see in the mark scheme they've drawn it out as a structure, or they've put the structural formula, and they've allowed different ways of illustrating that. Lots of different right answers for M. So we just went for that E isomer, and we showed that we could rotate that Ester link. I'm just having a look. You see that they've shown them all as Z isomers, I think. So not quite as easy to see, but this was I think this was the one that we went for to start with. and then this is the one where we've rotated the ester link. For N, you can see again a few possible answers there. This is the one that we showed, so we went for the 2 methyl groups. We said that if you use 2 hydrogens, then it was likely that you were going to be able to put some branching in, so you'd be able to get a branched carbon chain, and there were a couple. And then just note in the mark scheme, you might have done that, but you might have inadvertently made the answer to P, which was the optical isomer. So watch out for that. And then there's our answer to P. And again, so that was the only thing that was permissible for P. Okay, jolly good. Let's move on. So there's a slightly easier question 4 compared to 3, but this is a case of where there's only going to be one right answer. So it's an esters question. It gives us some information, but we're probably looking at the fact that we've got ethyl butanoate. So this is the ester that we want to make, and we need to make it in the first instance from an acid and an alcohol. I think probably what I'd be doing here is just be double checking that I drew ethyl butanoate and not butyl ethanoate. So I'm going to draw my ester out on the right hand side and make this as part of my equation. So ethyl means that that's the group attached to the oxygen, and so butanoate. Be careful about doing things like that. So this is now a little bit ambiguous on the left-hand side. So this could be branched, and you'll often see those penalised. So I'm just going to give the structure, which just means it takes a little bit longer. So CH3, CH2, CH2. So there's my ethyl butanoate, and I want to make it from an acid and an alcohol. So there's the alcohol, and there's the acid, just so that we're clear. So my acid, as you can see, is going to be butanoic acid. So CH3, CH2, CH2, COOH. I could have drawn the skeletal. I could have drawn them out as a displayed formula as well. And my alcohol just needs to be ethanol. So that and that make this. Will it let me move it all? I'm just moving that. Let's move that. I don't want that. No, I don't want to move that. That's. Come on. There we go. And we'll move the little clouds back. Nice. So if I'm being on my best behaviour, remember this is an equilibrium reaction. So I'll put my equilibrium signs in. I'm sure we'd get away if we just did a normal arrow. And then my other product, in this case, will be water. Write an equation, okay. 4 marks, you can see, seems pretty generous for this. Give a catalyst used for the reaction. You've probably learnt this from when you've done reaction conditions, but sulfuric acid, and you're probably thinking that it's concentrated sulfuric acid. Would imagine we'll get away with either, but I think I'd include the concentrated bit. Butyl ethanoate. So note our ester is the other way around now. So I've got butyl as the alcohol. Write an equation for the preparation of butyl ethanoate. Right, I think what I'll do this time, I'm going to draw it skeletally. So 1, 2, 3, 4. So that is butyl ethanoate. So 1, 2, 3, 4. And then my ethanoate is there. Now this is coming from an acid anhydride. Hopefully what we can see is that the purple part, the ethanoate, will be from the acid anhydride, so that my alcohol, and I'll just highlight that again, needs to be butan-1-ol. That will give me the butyl. Now the acid anhydride, a sensible choice. We can see that we want the 2 there, and I would make it a symmetrical acid anhydride. So we've got ethanoic anhydride. So that gives both of those groups. Just getting a little bit messy now. So my ethanoic anhydride plus my butan-1-ol, and that's going to make my butyl ethanoate. And the other product, I've been in skeletal, so I'll stay skeletal, is ethanoic acid. Write an equation for the preparation. So that's that. That's my 3 marks. Let's have a look and see where the mark scheme went with those 2 questions. Doesn't look like that one's been added in. Okay. Oh, we've not finished it yet. The ester shown below occurs in vegetable oils. Write an equation to show the formation of biodiesel from this ester. So similar to one that we've seen already. So I'm going to, I'll draw out the fat again. And in making biodiesel, we've said already, so we will use methanol, and the methanol, so we're going to break, so remember here's the Ester Links, we're going to break those Ester Links, and we're going to make an ester with the methanol instead. I'll just reverse those round again. So we did soap with this before. Now we're just making the methyl ester. So that's the first one. And then we've got it again. With C17H33. And then we've got it again with C17H29. Just getting a little bit squashed there. So those are the 3 molecules of biodiesel. To do that, we would have needed the 3 methanols, and my other product, of course, we get the glycerol, however you choose to show your glycerol. Like so. So a little bit scruffy. So we've got our three molecules of biodiesel along with our glycerol, and it required 3 methanol molecules. 3 marks for that. Aha, here's the mark scheme then. So going back to the equations to do the esterification, so we've got our butanoic acid and ethanol. So that was worth, you can see there, they didn't allow the C3H7. So we've got our marks for those, and then we got our marks for the products. And sulfuric acid is what they've gone for. You can see they've allowed hydrochloric or phosphoric as well, and not too bothered, so they put conc or dilute, or you didn't even have to say anything, but not nitric acid. And then they've not got the mark scheme there for the acid anhydride one that we did, so they've just skipped to the mark scheme for the transesterification. So there we've got the 3 methanols. These would be generally not particularly well answered, so it's a good area to make sure that you pick the marks up. And there we've got our 3 separate biodiesel molecules. Okay. Last one. So more with fats, and this time we've got some so similar to the first one. So we're making soap, we can see. So we're hydrolyzing the fat using sodium hydroxide. So the IUPAC name for glycerol, well, we've mentioned this already going through. So it's a triol, so 3 carbons, so propane or propan, doesn't matter which. So propane, 1, 2, 3. Triol, quite common, you'll see that as when you're going through the past paper questions quite a lot. Give a use for the mixture of the sodium salts. So the sodium salts are the long chain carboxylic acids, so that's all of those. And you can see also palm oil, bit of a clue here, so think palm olive, a big brand. So this is soap manufacture. When tea is heated with an excess of methanol, this looks like the transesterification again. So this is the biodiesel. So we've seen that in a couple of questions already. One of the methyl esters in the mixture. Now this looks like it's going to be awful, but basically all it's wanting is for us to draw 2 hydrogen atoms on there to show what the Z would mean in terms of its name. So they're going to be on the same side. No German accents, please. So our hydrogens are like so, and then our carbon chains are going to be going. So the carbon chains are going to take priority. So that will be the Z isomer. So a nice easy mark there. One of the other methyl esters has this formula, write an equation for the complete combustion. You could do it just as CH3, CH2, 12 times. So here's the ester. I might be tempted at this point just to lump all the carbons, the hydrogens and the oxygens together. Even underneath, even if I left that as my molecule in the equation, so I might be thinking I've got 2 oxygens, that's the easy bit. So I've got 1, 12, 13, 14 carbons, and then let's just get my hydrogens right. So I've got 24 from the CH2s, 25, 28. That might make it easier to balance. I'm obviously going to be reacting it with oxygen, and it's complete combustion, so we're going to make carbon dioxide and water. So 14 carbons, see it's a little bit easier just to see now I've done that with my molecule. 14 carbons, I've got 28 hydrogens, so that means I've got 14 waters as well, which gives me a total of 28 oxygens and my 14 from the waters, so that takes me to 42 oxygens. Remember, I've got 2 oxygens in my ester, so this needs to be account for 40 oxygens.
Sorry, Richard, have you got 15 carbons or 14?
So we should have that.
Sorry, Richard, can you hear me?
Let's have a look at the mark scheme. So propane 1, 2, 3 triol, so that's looking good. We've got the soaps, we've got the biodiesel, and
Sorry,
we've got
Richard,
the
can you hear me?
hydrogens. And down here it looks like I balanced it wrong. So we've got 15. Oh, brilliant. Well done, Richard. So 15 carbons. Let's just go back, see the mistake that I made. So it just shows that. So what was the point in doing that little trick? And it just shows you should have a look at the mark scheme before. So 1, 12, 13, 14, 15. What an idiot. Okay, sorry about that, guys. So C15, which means that we've got 24, 30 hydrogens. Oh dear, let's start again. So 30 hydrogens, this is all wrong. I'm sure you weren't paying any attention to me anyway. So forget about that last bit. Unbelievable. Right, okay, right, we're back on it. So that's 15, this is 15, pretend all that never happened. That means we've got 30, we've got 45 oxygens, and we've accounted for 2 of them already. So we need 43 oxygens from the O2, so that needs to be 21.5 or 43 over 2. Glad I got the balanced equation wrong. Okay, so hopefully Brendan has tackled any questions that you might have. So I think 45 minutes on that is quite long enough. Thanks for turning up. Come along next week. Okay, bye.